So yeah, we actually did not get a little bit of this done from yesterday. So I want to pick up on number 11. Okay, so when you're looking at number 11, the question says, determine if the following statements are true or false. Now remember this. Remember the parallelogram method I mentioned of adding vectors or whatever, or the end-to-end method of adding vectors? So on the end-to-end method, basically you take a vector, which I could just call, say, A, and I add it to another vector, maybe that's called B. Well, then from the beginning of the first, if they go like this, from the beginning of the first to the end of the second, that would be my resultant vector, right? So you would have to draw that arrow that way, and that would be A plus B. So if I gave you or I'm just going to call A plus B C. So if you saw a statement like this, everybody with me? This is arguably one of the more missed things on the test. Okay, so this would be a true statement if I said A plus B equals C, right? Because I've added vector A to vector B and got vector C. Are you with me? Now what if I did this? Is it true now? It's not, because A plus B should have a vector going this way, not a vector going this way. So this would be a false statement, wouldn't it? Now, is there anything I could do to this to make this thing be true? Negate C. Because if C is going this way, a negative C would have the same movements but in the opposite direction. So if that's regular C, then that right there would have been a negative C, and then again, A plus B would give me negative C. That would be true. So when you look at this picture, I'm asking you, are these statements true? And by the way, I can do this with more than two vectors, adding them and subtracting them. Like if I had A, B, and let's just say this was C. Then A plus B plus C equals what? That. So that would be A plus B plus C, or if you want to call it, you could call it D. So I could say, is this a true statement? Yeah, because A plus B plus C equaled D. But if this was the case, is that a true statement? No. What is a true statement from this? Can you give me a couple? Would this be true? Would A plus B equal C plus D? It actually would, right? Because A plus B gives me that. D plus C, or vice versa, gives me that. So that could be true. Would this also be true? I mean, from the math, right, you could just subtract the C and see that. But even if you didn't see this, if you just saw that, yeah, if I negate C and turn it around, is A plus B plus negative C equal to D? Okay, so that's all I'm asking you on these pictures, is to tell me if you can tell if these statements are true or false. So let's check out the first one. Here's A, there's B, and it looks like C is going that way. Y'all see that? So I'm telling you to add negative C to it. So let's make that negative C right here. Is A plus B plus C plus negative C, which would be that, is that the same thing as J plus G? Is it? These are the same thing, so true. Is E, right here, E plus D equal to F? No, because F's going the wrong way. So that would be false, but what would make it true? Negative F, or maybe negative E and negative D. All right, and then right here is G, which is this one, plus F, which is that one. Is that equal to H? Yes, that looks true to me. And is H plus E plus D, here's H, here's E, there's D. Is that equal to G? Yes. So I'm asking you, do you understand these things, and are you able to kind of comprehend them? And this is totally an end-to-end method, not a parallelogram method thing at all. Now in this last one, and this is where having vectors in component form are really helpful. I've given you the same kind of situation with A, B, C, D, and E, and I've got vectors going different ways. But here I'm saying, what's A plus B plus C? Is that the same thing as D plus E? Is D plus E the same thing as E plus D? Yes. Yeah, because, watch this. That's E and D would give me this, right? You with me? E and D would give me that, if I added them together, which is the vector 1, 2, 3, 4, 5, 6, 7, -3. Right? Well, look, if I took D and added an E to it. E is 1, 2, 3, 1, 2, 3, 4, -5. So from here, if I went 1, 2, 3, 1, 2, 3, 4, -5. So is that the same thing as the other one? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. Gives you the same thing. So D plus E and E plus D, same difference. So is that true? Yeah, it would have to be true because ABC puts me right here, and adding D and E puts me right there. Is ABCD equal to E? A, B, C. Now that's positive D, right? What would be equal to E? Yeah, if I turned D around and made it -D. So that would be true. Y'all seeing these? Okay, so you might see a little bit of that and on your test. We'll see what happens. Okay, so here is what I want to talk about today is trig form. And trig form of a vector, I used to actually do log cosines first. And I would give you all kind of weird situations like, hey, if a plane was going this way and a wind was blowing on it this way, and how would it push the thing off? And you used to have to actually draw these diagrams and how wind was affecting the plane's travel, or maybe like if you're rowing your boat across a river and the river's going downstream, what would be the final result? And you have to draw all these angles, and you have to pull out all this trig and all this geometry that you learned about alternate interior angles are congruent and blah, blah, blah. And people would get lost in the geometry. And it was really hard. And then I started switching it up and doing vectors first. Because if you could take something that's moving in a certain direction at a certain speed, or like angles with lengths, and if you can draw your picture kind of like we were just doing, but you write it as components, then you can just add the components up and get results out of that. That's kind of what we're doing today. And you're going to see this is not overly difficult, but it would be really difficult if you had to draw pictures. And we're going to avoid all that because we're going to learn vectors before we get to law of sines and cosines. So what I want to talk today is a little bit more about trig form. Now, you remember that problem I did yesterday where I gave something to you in trig form, like, where is it? Well, I guess I don't really have it here. Oh, right there. Remember I gave something like that and I said, hey, what's the magnitude and what's the direction angle? And I showed you what I don't want you to do, which is multiply it out. Remember that when we did that? Okay, I want you to just see that. But right now I want you to show you that if I give you that vector and that angle, make sure you understand the process of taking a direction angle and taking a magnitude and getting the components, right? And then once you have your components, you can tack i's and j's on them if you want, or have it in component form and you're ready to actually do the math. But if you really think about the order that you're doing this, what you're really doing is kind of going from trig form, and you're going to see this down here at the bottom. If I give you information like a magnitude and a direction angle, you're really going from trig form to unit vector form to component form. I mean, you don't have to, but that's kind of the mentality. So right here, trig form, you're going to take the magnitude, parentheses, cosine of the angle times I, to let you know that you're moving left and right, plus sine of the angle times j. And that's trig form. And then all you have to do with trig form to go to unit vector form is do what? Distribute it in. And simplify it if you want. So right here, 15 cosine 115i plus 15 sine 115j is technically my unit vector form. But if I wanted to make decimals out of it, great. And then once it's in this form, if I wanted to go to component form, I would just what? Drop the I, drop the J, drop the plus, and then what do you put in there? The weird brackets and a comma. And again, if you had a calculator, which you may or may not on this test, I'm kind of feeling not. If you had a calculator, you would want to just maybe write it around the decimals, but if you don't, you just leave it like this. So on all of these, the same kind of process holds. I'll jump to this last one. Right here, start with 3.4 on the outside of a parentheses, cosine 87i plus sine 87j. Then, for unit vector form, distribute it in, 3.4 cosine 87i, 3.4 sine 87j, and then finally, for component form, 3.4 cosine 87, 3.4 sine 87. And bracket. So hopefully that's not a big deal. But what we're going to be doing today is talking about some word problems where this comes into play. So you're going to be given information like, hey, you're flying a plane at 400 miles per hour. And hopefully that's like, oh, that's a rate, or I mean, that's a velocity or a speed or whatever. That's a magnitude. And you're flying at a direction angle of 20 degrees. Oh, there's your angle. Well, I could draw a picture of that and try to make sense of it and figure out where my result is, you know, after some other operation is working against it, like wind or something like that. But that becomes a lot more difficult. But if I can just change them to components, then I can just add them or subtract them and come up with a new resultant vector, kind of like what I've been doing, except pictures stink, right? But I can come up with a new resultant vector that I can now take and convert back into direction and magnitude if I need it. So let's check this out. First word problem on number 1. I'm just going to walk you through the process so hopefully you'll see it. So let's just say a pilot is directing his plane with the direction vector of, or direction, I should have said angle, sorry, a direction angle of 132 degrees. So that would be kind of like me, if that's pointing at 0, 132 might be something like that, okay? So I'm flying at 132 degrees, and the instrument gauge on the plane reads 450 miles per hour. So we're going to say the magnitude is 450, and the direction angle was 132. Then, along comes a wind. He's being blown off course or whatever. Maybe he's up there in the jet stream, which can hit speeds of over 100 miles an hour. You know, you're up there like it's like the East Australian current from Finding Nemo. You know, you get up in there and it just kind of carries you along. So he's being blown off course by an 85 mile per hour wind with the direction vector of 67. So if I was going to tack this vector onto that vector, I would have to say, well, what does 67 look like? Kind of like this. So I would tack it onto the end of this right here and say, all right, 67 would look maybe like that, except the magnitude would make this vector a lot smaller than this, maybe a fifth the size. So here's the here's what the plane wants to do or thinks it's doing, but the wind is constantly blowing on it. Well, he really didn't travel in that direction then, did he? Right, so he ended up getting pushed off. Now, granted, don't think this too. It's not like the plane flies here and then goes, okay, wind, and then just gets blown to there. That's not what it works. He's going to be moving gradually where? Towards that, the result. Now, if I had to do this manually to find that new angle and that new magnitude, that would be tricky. Because I would have to set this up and say, okay, I have to figure out something about this inner triangle to be able to find that side. And then I would have to find out that little angle right there to be able to subtract it from 132 to find that angle. It becomes a mess from that standpoint of trig and geometry. But from the standpoint of vectors, it's super easy. Because we just said that that vector added to that vector gives me the resultant vector. So if I can just turn these two purple vectors into component form, or maybe unit vector form, then it's easy to add them together, right? And when I add the two together, I get the result. And then once I get the result, I can take that component and go backwards and find the magnitude and the direction. So here would be my process. Am I making sense? Okay, so here's my process. The plane vector, I'm going to call it P. The magnitude of P, they gave it to me 450, and they gave me the direction angle. So to convert P into a vector, I can kind of do what I just did on my trig form sheet. Now you can jump straight to here if you want, but essentially I'm saying magnitude, cosine theta I plus sine theta j, and I'm going to multiply the 450 in and simplify. Now if you want to jump straight to here by going 450 cosine of the angle, bam. 450 sine of the 132, bam. And put it straight there, great. That's what I would do. But this is essentially what I'm doing. That's vector P. And you can kind of see it, right? Negative 300 something, positive 300 something. All right, then you do the wind vector. All right, so the wind vector over here, the wind vector says, all right, 85 with a angle right there of 60, what did we say, 67. All right, so I'm going to do the same thing again. Magnitude cosine angle I plus sine angle j. But I'm just going to probably, if it's me, go magnitude cosine of the angle, bam. Magnitude sine of the angle, and put it there. And now I have my plane and my wind vector. And what happens when a plane and wind act together? You get a different result, right? So all I got to do now is add the P and the W. And I did that right here. To add the P and the W, I add the X components, I add the Y components, and that is my result, right? The resultant vector is plane plus W. You with me? Now, the question was not find the resultant vector. What was the question? Find the direction it's going to really head and how fast it's going to really go. Well, what is that asking? Magnitude and direction angle. So, back to my result. I take that and square it. I take that and square it. I add it together and square root it. So it turns out I'm actually going faster than my speedometer was. So I'm actually going 491.99 miles an hour. And for the direction angle, inverse tangent of y over x, which is going to give me negative 57, but why do I have to add a 180? Because I went left, which puts me in the wrong quadrant for tangent to answer that question correctly. So I add a 180. So it turns out I'm not actually going at 132 degrees, I'm going at 122.99 degrees as a direction angle, and I'm going 491.99 miles per hour. And think about it, what would you do right here if you did not have vectors? I mean, you have law of sines and cosines, but do you know anything about this other than this side and this side? You don't even know that interior angle, do you? Are you following what I'm saying? This becomes a much more tricky problem than you think. Now, you can do it. There are ways to do it, but you end up having to draw all kinds of things. You have to do stuff like this. Okay, there's a horizontal. There's a horizontal. So if this is 132 here, then doesn't that make that 132 there? Who would have thought of that? Crickets, right? And if that's 132 here, what's that little part here? That would be a supplement. So that would be what, 48? Well, if that's 48 and that's 67, I guess I know this whole interior angle would be 115. Side, angle, side. And at that point, you could pull out law of cosines and solve. But are you hearing what I'm saying? I mean, that's much more difficult to think through, and I still got to pull out law of cosines, potentially law of sines, make sure I don't get any ambiguous case. I don't have to deal with any of that with vectors. All I got to make sure I know is P plus W. When you have a plane and you add a wind, it gives you a result, right? Plane plus the wind equals the result. You tracking? Okay, what do I got? 5 minutes. Let's see if we can walk through one of these quickly. All right, from the south, at least get it set up. From the south end of a river, flowing east to west. So draw a good picture. I'm flowing east towards the west, right? So I'm flowing that way. From the south end All right, so right here, I'm from the south end, Biff dives into the river. All right, so he dives into the river. Remember, the river's flowing this way at an angle of 31 degrees from the east. So from the east, that's east, 31 degrees. You follow me? So he dives in at that angle. That's his vector, 31. And he swims at a rate of 3 miles an hour. So that's his magnitude, 3. All right, now, the river's flowing to the west at a rate of 1 mile an hour. So this is actually a terrible picture for people who are watching at home. So dives into the river at an angle of 31 degrees at 3 miles an hour, but the river is flowing that way at 1 mile an hour. Now, what is the direction angle of the river then? The river, 180, because west is 180 degrees. So you got to know that. You got to be able to think through that. So that would be 180 degrees. So can you find, and the question is saying, how fast is he actually moving? Well, if he's swimming this way, he's actually that one would probably look more like that line. He's really not going in that direction, is he? Because the current's fighting against him. So he really ends up going there. So the question is, what's his magnitude and what is his real direction angle? So can I find the two vectors? Can I find the Biff vector?
Yeah.
The Biff vector would be what? What's the Biff vector? 3 cosine 31, comma 3 sine 31. Great, there's my Biff vector. Can I find the current vector? What's the current vector? 1 cosine, yeah, you don't need the 180. 1 sine 180. And then what would be the result of this? So the result is whatever the Biff plus the current is. Yeah?
On the test, if we don't have a calculator, you want us to
I'd give you better stuff on the calculator. Yeah. Or I would, you'll see. I give a decent review sheet where you'll get that question answered. He's asking, what would I do if I didn't have a calculator? I usually say, set up what you would do, and then another one I'll go, if this, and I'll give you values and ask you how you close the deal. So it'll make sense. So right here, the resultant vector gives, I have to now go 3 cosine 31, whatever that is, right? And I'm going to have to add that to this. Now I happen to know what 1 cosine 180 is. It is -1. And then I'm going to go 3 sine 31, whatever that is, probably close to 1.5. And then I'm going to go sine of 180. What's sine of 180? 0. And whatever that gives me is my resultant vector. And then once I get that resultant vector right there, I have time. Okay, so 3 cosine 31, 2.571-ish, 2.571, actually 1.5, and then 3 sine 31, 1.545. Oh, I did not. Minus 1, 1.5715, and then 1.545. So clearly my picture was not great because it really probably looks more like a 45 degree angle. It should have been going more like that, but doesn't matter. I didn't have to draw a good picture because I understood the situation, right? And then now that I have the result, how fast was he really going? That's my magnitude. So I'm going to square that, and you can be exact in this case, guys. You can go up here, and you can go grab your values. You know that you can move back up with your calculator and enter it and bring it down so you don't have to do any rounding. So I'm going to do that. I'm going to bring that down and square it, and then go plus, and then bring the other one down and square it. And then I'm going to square root that answer. So you should get 2.204. What are we talking about? Miles per hour. And then how do I do the direction angle? Inverse tan of y over x, 1.545 over 1.5715. And I don't have to add 180 because it's not negative in the x coordinate, and that's going to give me something pretty close to probably pretty close to 45 degrees, I'm guessing. So I'm gonna take that 1.545 and that 1.5715 and 44.51 ish. We'll call it that. Track with me? Okay, that's the idea. Let me caution you about one thing tonight. You remember the plane and the wind vector? Okay, we said that the plane plus the wind gave me the result. There's one problem in your homework where I say this. I give you the result. Like I give you where he wants to end up going. And then I tell you what the wind is. And I ask you, where does the pilot need to direct his plane so that the wind will push him to the right place? What would I be solving for here? R minus W. So just be aware of that on one of these problems. I don't think you need to watch any video. Nice. All right.
Third up.
Speeding up.
Third up.